Right now, across global enterprise networks, employees are actively leaking confidential data. Industry audits reveal that 11% of all generative AI prompts contain proprietary corporate information. This is the crisis of shadow AI. It happens through a simple, everyday operational habit. An analyst needs a summary, so they copy the text of an unredacted non-disclosure agreement, a patient file, or raw application code, and paste it directly into the input field of a web-based tool like ChatGPT or Claude. This introduces a threat known as contextual PII. Unlike structured data neatly organized in rows and columns of a database, contextual PII is buried within paragraphs of conversational text. It is a name tied to a medical diagnosis or a financial figure embedded in legal terminology. Traditional network firewalls are highly effective at blocking unauthorized IP addresses or malicious executables, but they are structurally blind to unstructured, semantic text traveling outbound in a standard web request. The firewall cleanly intercepts structured packets. However, modern AI interactions use standard HTTPS. The firewall cannot parse this continuous stream of encrypted conversational text. As a result, proprietary data bypasses the perimeter, landing on external cloud servers to be logged or used for training. To patch this massive leak, the cybersecurity industry defaulted to a familiar architecture, routing all outbound AI traffic through Cloud Data Loss Prevention, or DLP, proxies. In theory, a cloud DLP acts as a middleman. It catches the outbound prompt, uses an API to scan the text for sensitive information, scrubs it, and then forwards the sanitized version to the AI provider. But this creates an immediate architectural contradiction. You are attempting to protect sensitive, local data by actively transmitting it across the internet to yet another third-party server. Routing traffic through a cloud proxy doesn't eliminate the risk. It introduces a second vendor into the data lifecycle. To achieve actual security, the network transit must be eliminated entirely. Let's break down the required network topology of a standard cloud DLP API integration to understand exactly where it fails under the demands of generative AI. On this topology map, a user's plain text packet traverses the wide area network to the proxy provider's node. It sits on a foreign server while algorithms filter identities. Once processed, the scrubbed data routes back through the network, then finally out to the LLM endpoint. This multi-hop transit structurally violates the core tenet of data minimization. Data minimization mandates that sensitive information should be exposed to as few systems as possible. Cloud DLP requires you to upload your sensitive context to a secondary vendor simply to hide it from the primary AI vendor. Sending unredacted text to a third-party API means you now have two vendors processing confidential data, requiring two separate legal reviews and security audits. Beyond the compliance exposure, this multi-hop architecture introduces a second major flaw for end users: severe API latency. Notice the delay introduced by this routing. A round-trip network webhook call to a cloud DLP API imposes a processing penalty of anywhere from 500 to 2,500 milliseconds per prompt. When you add 2.5 seconds of network delay to the generation time of the language model itself, it ruins the real-time experience of the chatbot. Users experience friction, and when security creates friction, employees find workarounds. Firm conclusion: Cloud DLP forces a trade-off between performance and privacy, creating new data hops that legacy tools were never designed to handle. The modern architectural alternative is Zero-Trust Data Sanitization, or ZTDS. Returning to our tautology map, we shift focus entirely to the local machine's hardware. ZTDS cuts the external proxy connection. When an employee pastes text, the browser's DOM intercepts the payload at the keyboard level, securing data before opening a network socket. This requires a highly specific execution environment. Instead of calling an external server, ZTDS runs directly inside the local browser using vanilla JavaScript and WebAssembly. Inside this volatile RAM sandbox, raw identifiers like names, emails, and social security numbers are instantly converted into structured placeholder tokens, like Name1 or Financial1. Because this happens strictly inside the local hardware cache, the 2,500 millisecond cloud penalty is eliminated. Text is tokenized locally in under 15 milliseconds. Intriguing. The verification for this architecture isn't found in a vendor's privacy policy. It is proven through a test standard known as airplane mode verification. If you disconnect your computer from the internet entirely, enable airplane mode, and paste sensitive data into the browser, the ZTDS engine still executes flawlessly. This capability provides empirical proof that sanitization occurs locally without any external network dependency. Because the code runs offline, it is physically impossible for the tool to generate server logs or phone home with telemetry data. By isolating and pseudonymizing personal data precisely at its point of origin, ZTDS removes the cloud from the trust equation. Erasing data locally solves the security problem, but it introduces an operational one. If you strip out all the nouns and numbers, the language model loses the context it needs to provide an accurate analysis. ZTDS solves this through deterministic tokenization. By replacing specific data with consistent, formatted placeholders, the semantic structure is preserved. The LLM knows it is analyzing a contract between Company A and Company B, even though it never sees their actual names. We can see this in transit. A secured packet containing only placeholder tokens travels to the LLM cloud, while the original plaintext remains locked in local RAM. The language model performs its analysis and sends a response back featuring those exact same placeholder tokens. When that response arrives at the local browser, ZTDS initiates a protocol called reverse scrubbing. The browser references a temporary dictionary held securely in your local memory. It maps the tokens in the AI's response against this dictionary and instantly translates them back into the original plaintext data right before your eyes. Note that this local dictionary is entirely volatile. The moment the user closes the browser tab, the original identifiers and the mapping keys cease to exist. The workflow is unbroken. The enterprise harnesses the full analytical power of generative AI, while the AI provider remains mathematically isolated from the proprietary data. Enterprise AI security requires a pivot from network monitoring to local execution. We can no longer rely on the strategy of uploading sensitive context to a third-party server just to protect it. Protection must happen where the data originates. Adopting a strictly local architecture yields specific regulatory advantages. By keeping data processing client-side, the burden of centralized compliance auditing drops significantly. Because no data leaves the endpoint unencrypted, local execution satisfies SOC 2 Type 2 boundary protection controls without requiring new infrastructure. It aligns with the de-identification standards of HIPAA Safe Harbor and automates the data minimization requirements of GDPR. This comparative matrix illustrates why. By bypassing cloud transit, the data transfer is legally exempt from the data processing agreements and vendor risk assessments required by legacy cloud DLP systems. Today, generative AI moves the point of exfiltration from a predictable database query to an unpredictable open user prompt. The defense can no longer be thought of as a network-wide firewall or a cloud proxy inspecting packets in transit. Those defenses operate outside the context of the prompt. The new boundary is the semantic layer inside local memory. By isolating data in volatile RAM, the identity remains separated from the outbound request. To maintain enterprise compliance, sanitization must occur before the data ever reaches the internet. Organizations can now adopt AI by moving the trust boundary from the cloud back to the local machine.